Ancestors of mammals, Synapsids, and the Permian Period Gorgonopsids. The deep time perspective. When we imagine the prehistoric past, the popular imagination almost invariably drifts toward the Mesozoic Era, the age of the dinosaurs. We envision the thundering footsteps of the Tyrannosaurus rex, or the towering necks of the sauropods. However, long before the first dinosaur hatched from an egg, the Earth was dominated by a different dynasty of giants. These were the Synapsids, a group often clumsily referred to as mammal-like reptiles, though they were not reptiles at all in the cladistic sense. They were the stem-mammals, the direct ancestors and cousins of the lineage that would eventually produce humanity. Among this diverse and spectacular radiation of animals, one group stood out as the supreme apex predators of their time. They were the Gorgonopsids, the first true sabertooths of Earth history, and the terrors of the Permian Period. To understand the Gorgonopsids is to understand a lost world that existed between 299 million and 252 million years ago, a world that ended in the greatest catastrophe life has ever known. This text serves as a comprehensive exploration of that time, tracing the evolutionary path from the earliest amniotes to the specialized hunters that ruled the supercontinent of Pangaea. The origin of Synapsids. To understand the Gorgonopsids, one must first understand the larger family to which they belonged. The story begins in the Carboniferous period, a time of vast swamps and high atmospheric oxygen. It was here that the early tetrapods, four-limbed vertebrates that had crawled out of the water, made a crucial evolutionary leap. They developed the amniotic egg. This hard-shelled or leathery egg contained a portable pond, a fluid-filled sac that allowed embryos to develop on dry land without the need to return to the water to reproduce. This innovation split the tetrapods into two distinct lineages that would diverge forever. One line was the Sauropsida, which would eventually lead to modern reptiles, dinosaurs, and birds. The other line was the Synapsida. The defining characteristic that separates a synapsid from a sauropsid is a subtle feature of the skull. Synapsids possess a single opening in the skull behind the eye socket, known as the temporal fenestra. This opening was not a defect, but an adaptation. It lightened the skull and provided an anchor point for stronger jaw muscles, allowing for a more powerful bite. Every mammal alive today, from the blue whale to the bumblebee bat to the human being, possesses this synapsid skull structure, although it has been highly modified over millions of years. In the Carboniferous and early Permian, these early synapsids were the dominant land animals, the pelycosaur grade. The earliest synapsids are often grouped together in a paraphyletic grade known informally as pelycosaurs. The most famous of these is Dimetrodon, a creature frequently and incorrectly included in toy dinosaur sets. Dimetrodon was not a dinosaur. It was a stem mammal, closer to a human than to a triceratops. These animals ruled the early Permian. They were characterized by a sprawling gait, their bellies close to the ground, and their limbs jutting out to the sides like those of a lizard. Many, like Dimetrodon and Edaphosaurus, evolved elaborate sails on their backs, formed by elongated neural spines. These sails were likely used for thermoregulation, allowing the animals to warm up quickly in the morning sun, or for sexual display. While pelycosaurs were successful, they were evolutionarily primitive. Their teeth were generally undifferentiated, meaning they looked mostly the same throughout the jaw, although Dimetrodon showed the beginnings of specialized teeth, a trait known as heterodonty. As the Permian period progressed, the climate of the Earth began to change. The continents were drifting together to form the supercontinent Pangaea, and the world was becoming drier and hotter. The swampy forests of the Carboniferous were replaced by vast interiors of arid scrub and desert. In this changing world, the pelycosaurs began to fade, and a new, more advanced group of synapsids emerged to take their place. These were the Therapsids. The Therapsid Revolution. The Therapsids, appearing in the Middle Permian, represented a quantum leap in synapsid evolution. They are the group that includes the Gorgonopsids, as well as the direct ancestors of mammals. Therapsids fundamentally reorganized the synapsid body plan. The sprawling limbs of the pelycosaurs were rotated underneath the body, providing a more semi-erect posture. This anatomical shift allowed for more efficient locomotion and perhaps greater stamina. The skull became more specialized, and the temporal fenestra expanded to accommodate even larger jaw muscles. Crucially, Therapsids developed complex heterodonty. Instead of a jaw full of identical pegs, they developed distinct incisors for nipping, canines for piercing, and post-canine teeth for shearing or grinding. This dental specialization allowed Therapsids to process food more efficiently than their predecessors, extracting more energy to fuel a metabolism that was becoming increasingly active. There is significant debate among paleontologists regarding the thermal physiology of early Therapsids. While they were likely not endothermic, warm-blooded, in the modern mammalian sense, they were almost certainly not sluggish ectotherms, cold-blooded, like modern lizards. They likely occupied a middle ground, possessing elevated metabolic rates that allowed for sustained activity. It was from this diverse and innovative stock that the Gorgonopsids evolved. Taxonomy and discovery of Gorgonopsia. The clade Gorgonopsia falls within the suborder Theriodontia, which translates to beast tooth, a fitting name given their dental armaments. The first Gorgonopsid fossils were described in the late 19th century by Sir Richard Owen, the same scientist who coined the word dinosaur. The type specimen, Gorgonops torvus, was discovered in the Karoo Basin of South Africa, a geological treasure trove that has provided an almost unbroken record of life on land from the Middle Permian to the early Jurassic. The name Gorgonops is derived from the Gorgons of Greek mythology, terrifying monsters capable of turning men to stone with a glance, and ops, meaning face or eye. Thus, they were the Gorgon faces. Since that initial discovery, dozens of genera have been identified, ranging from small, dog-sized predators to massive, bear-sized killers. The majority of these fossils come from two primary locations: the Karoo supergroup in South Africa and the Permian sedimentary rocks of the Russian platform. These two regions, though now separated by thousands of miles, were connected during the Permian as part of Pangaea. The similarity between the fauna of South Africa and Russia provides crucial evidence for the theory of continental drift and allows scientists to reconstruct the global ecosystem of the late Permian. Anatomy of a killer. To visualize a Gorgonopsid, one must strip away the image of a modern lion or wolf and assemble a creature that is a mosaic of reptilian and mammalian features. The most striking feature of the Gorgonopsid was its skull. It was generally long, deep, and box-like in shape. The snout was elongated to accommodate large respiratory passages, suggesting a reliance on scent and a need for high oxygen intake. The defining weapon of the Gorgonopsid was its pair of hypertrophied canine teeth. In the upper jaw, these sabers grew to immense lengths, extending far past the lower jaw when the mouth was closed. In some species, such as the giant Inostrantsevia, these canines could reach lengths of 15 centimeters. These were not round, conical teeth like those of a crocodile. They were transversely compressed and serrated along the edges, functioning like steak knives designed to slice through thick hide and flesh. The lower jaw often featured a protective flange of bone that the upper canines would rest against, a feature that anticipated the chin shapes of later sabertooth cats like Smilodon. However, unlike cats, Gorgonopsids did not have specialized shearing teeth in the back of the jaw called carnassials. Their post-canine teeth were often reduced in number and size, suggesting that they did not chew their food extensively but rather tore off large chunks and swallowed them whole. The post-cranial skeleton. Behind the massive head lay a body built for power. Gorgonopsids possessed a robust skeleton. Their neck vertebrae were thick and strong, anchoring powerful muscles required to drive the skull downwards and drag prey. The shoulder girdle was massive, providing a stable platform for the forelimbs. The limb posture of Gorgonopsids is a subject of interesting biomechanical analysis. The hind limbs were likely held in a semi-erect or erect posture, moving mostly parallel to the body, much like a mammal. The forelimbs, however, retained a somewhat more sprawling posture, with the elbows jutting slightly outward. This mosaic posture suggests an animal that was capable of sudden bursts of speed, but perhaps not the long-distance endurance running seen in modern wolves. The feet were plantigrade, meaning they walked on their palms and soles rather than their toes. They had 5 digits on each foot, likely tipped with sharp claws. The tail was moderately long but reduced compared to the heavy tails of reptiles, as it was no longer needed as a counterweight for the legs due to the more upright posture. The skin of Gorgonopsids remains a mystery. For decades, they were depicted with scaly reptilian skin. However, recent discoveries of coprolites, fossilized dung, containing hair-like structures in the Permian, along with the presence of small pits on the snout of Gorgonopsid skulls that resemble the whisker pits of mammals, have led to a shift in perception. It is now considered scientifically plausible, if not probable, that Gorgonopsids possessed vibrissae, whiskers, and perhaps a coat of fur or fur-like filaments. This insulation would have been advantageous for an animal with a rising metabolism, helping to retain body heat. The ecological hierarchy. In the late Permian ecosystem, Gorgonopsids occupied the niche of the apex predator. They were the top of the food chain. To understand their role, we must look at the animals they hunted. The herbivores of the late Permian were diverse and abundant. The most common were the dicynodonts, another group of therapsids. Dicynodonts ranged from small burrowers like Diectodon to large grazers like Allocephalodon. They possessed turtle-like beaks and 2 large tusks. Alongside the dicynodonts were the Dinosaurs, massive armored parareptiles that looked somewhat like ugly knobby hippos. Cladistic, a famous parasaur from Russia, was a heavily built tank of an animal. Gorgonopsids were the only predators equipped to take down these large herbivores. A hunting Gorgonopsid likely relied on ambush tactics. With their slightly sprawling forelimbs, they were not built for prolonged chases. Instead, they would have utilized the cover of the fern forests or the rough terrain to get close to their prey. Once in range, they would launch a high-speed attack, using their immense weight to topple the victim. The killing bite was likely delivered to the neck. The saber-teeth were driven into the soft tissue, severing major blood vessels and the trachea. This slash-and-bleed tactic differs from the suffocation bite of modern lions, which clamp down on the windpipe. The serrated teeth of the Gorgonopsid would have caused massive blood loss, bringing down even the thick-skinned parasaurs relatively quickly. Specific genera, Inostrancevia. Among the Gorgonopsids, the genus Inostrancevia stands out as the ultimate expression of this predatory lineage. Discovered in the northern Dvina River excavations in Russia by Vladimir Amalitsky at the turn of the 20th century, Inostrancevia alexandri was a monster. It measured nearly 3.5 meters in length and weighed heavily. Its skull alone was over 45 centimeters long. The canines of Inostrancevia were terrifyingly large, capable of piercing the osteoderms, bony armor, of the parasaurs found in the same deposits. The discovery of Inostrancevia revealed that Gorgonopsids were not just mid-sized hunters, but had scaled up to become the largest terrestrial predators the Earth had seen up to that point. The sheer size of the temporal fenestra in Inostrancevia indicates massive adductor muscles, giving it a bite force that would have crushed bone. Fossil evidence suggests that these animals lived alongside the massive herbivore Scutosaurus. Several Scutosaurus skeletons have been found in association with Inostrancevia teeth, painting a vivid picture of life and death on the Russian floodplains. Specific genera: Lycanops and Rubidia. In the southern hemisphere, the Karoo Basin hosted a variety of forms. Lycanops, meaning wolf face, is perhaps the quintessential Gorgonopsid. Smaller than Inostrancevia, roughly the size of a large wolf or small lion, Lycanops was built for speed. Its skeleton shows a long, slender build, with limbs well adapted for running. It likely hunted the smaller Dicynodonts and fast-moving reptiles of the South African plains. At the other end of the spectrum in the Karoo was Rubidia. A member of the subfamily Rubidianae, this animal was the T-Rex of the African Permian. It had a massive, heavily ossified skull. Unlike the more slender snout of Lycanops, Rubidia had a broad, powerful head that could withstand immense stress. The Rubidians were the last and largest of the African Gorgonopsids, evolving just before the Great Extinction Event. Their robust construction suggests they were tackling the largest prey available, such as the giant Dicynodont Daptocephalus. Sensory biology. How did these animals perceive their world? The structure of the Gorgonopsid brain case gives us clues. While their brains were small compared to modern mammals, they were larger than those of their pelycosaur ancestors. The shape of the brain case suggests a well-developed flocculus, a region of the brain associated with balance and coordination of eye movement. This is consistent with an active, predatory lifestyle. The nasal cavity was large, implying a keen sense of smell. In a world without the thick grasslands of today, where prey might be hidden in dense scrub or at great distances across arid flats, scent would have been a primary tracking tool. The orbits, eye sockets, were positioned on the sides of the skull, but angled slightly forward, suggesting a degree of binocular vision, which is essential for depth perception when striking at prey. The pineal eye, a light-sensitive organ on the top of the head found in many primitive tetrapods, was still present in Gorgonopsids. This third eye likely helped regulate their circadian rhythms and hormonal cycles, synchronizing their activity with the day-night cycle of the Permian. The physiology debate. The question of whether Gorgonopsids were warm-blooded is central to understanding their biology. Modern science does not view warm-bloodedness, endothermy, and cold-bloodedness, ectothermy, as a simple binary switch, but rather as a spectrum. Gorgonopsids likely sat somewhere on the mesothermic to endothermic side of the scale. Evidence for this comes from bone histology. Slices of Gorgonopsid bone reveal a fibrolamellar texture, a type of bone tissue that is deposited rapidly. This rapid growth rate is a hallmark of high metabolic rates. Furthermore, the presence of respiratory turbinates, delicate scrolls of bone in the nasal cavity that warm and humidify inhaled air, is a subject of debate. Some scans suggest incipient ridges that could have supported such structures. If they had high metabolic rates, they would have needed to eat significantly more than a reptile of similar size. This constant need for fuel would have driven the evolutionary pressure for more efficient locomotion and more effective killing tools. They lived life in the fast lane compared to the lumbering parasaurs. The Permian world. The stage upon which the Gorgonopsids played out their drama was a world of extremes. By the late Permian, the supercontinent Pangaea was fully assembled, stretching from pole to pole. This vast landmass created extreme weather patterns. The interior of the continent was far from the moderating influence of the ocean, leading to hyper-arid deserts with extreme temperature fluctuations. However, there were also regions of seasonal monsoons, where torrential rains would flood the landscape, creating temporary lakes and lush vegetation before drying out again. It was a world of ferns, horsetails, and early gymnosperms. There were no flowering plants, no grasses, and no broad-leafed trees. The soundscape would have been different, too, with no birds to sing and no crickets to chirp, as many modern insect groups had not yet evolved. The dominant sounds would have been the wind, the rustle of dry vegetation, and the low, guttural bellows of synapsids, social behavior and reproduction. Inferring social behavior from fossils is notoriously difficult, but we can make educated guesses based on anatomy and comparison with modern analogs. Were Gorgonopsids solitary hunters or pack animals? The smaller species like Lycanops might have been pack hunters, cooperating to bring down prey larger than themselves, much like wolves or wild dogs. The larger forms like Inostrancevia and Rubegia were more likely solitary, territorial animals, coming together only to mate. The presence of healed bite marks on Gorgonopsid skulls suggests intraspecific combat, fighting among their own kind. This could have been for territory, mating rights, or carcasses. Regarding reproduction, Gorgonopsids were amniotes and almost certainly laid eggs. However, unlike the soft, parchment-like eggs of many reptiles, synapsid eggs might have been somewhat distinct. Parental care is another area of speculation. Given the higher investment in offspring required by animals with higher metabolic rates, it is plausible that Gorgonopsid parents guarded their nests and perhaps even provisioned their hatchlings for a time. This would mark the beginning of the deep bond between parent and offspring that characterizes the mammalian lineage. The Great Dying. The reign of the Gorgonopsids was brought to a sudden and catastrophic end approximately 252 million years ago. This was the Permian-Triassic extinction event, colloquially known as the Great Dying. It was the most severe extinction event in Earth's history, wiping out roughly 90% of all marine species and 70% of terrestrial vertebrate species. The primary culprit was a massive volcanic event in what is now Siberia, known as the Siberian Traps. This was not a single volcano but a flood basalt eruption that continued for hundreds of thousands of years, covering an area the size of the United States in lava. The immediate effect was the destruction of the local ecosystem, but the global effects were apocalyptic. The eruptions released colossal amounts of carbon dioxide and methane into the atmosphere. This triggered a runaway greenhouse effect. Global temperatures soared, the oceans acidified, and circulation currents stalled, leading to anoxic, oxygen-depleted waters that killed off marine life. The mechanism of extinction on land. On land, the situation was dire. The rapid warming disrupted weather patterns, leading to prolonged megadroughts and acid rain that stripped the land of vegetation. For top predators like the Gorgonopsids, this was a death sentence. The extinction cascade began at the bottom of the food chain. As plants died off due to aridity and acid rain, the large herbivores like parasaurs and decinodonts began to starve and die. With the crash in prey populations, the Gorgonopsids faced a calorie crisis. Their high metabolic rates, which had been their greatest strength, became their greatest liability. They could not simply slow down and wait out the famine like a crocodile could. They needed constant fuel. Furthermore, atmospheric oxygen levels plummeted during the transition. Gorgonopsids, with their large bodies and high oxygen demands, would have struggled to breathe in the thinning air. They were literally gasping for breath in a hot, dying world. The largest, most specialized species vanished first. The intricate food webs of the Permian collapsed completely. The fall of the Gorgonopsids. The fossil record shows a sharp cutoff. In the rocks marking the boundary between the Permian and the Triassic, the Gorgonopsid fossils simply disappear. They did not evolve into something else. They went extinct. The lineage that had produced the first saber-toothed killers was snuffed out. Their disappearance left a vacuum in the ecosystem. For a brief period in the early Triassic, the world was a disaster zone, populated by a few hardy survivors like the genus Lystrosaurus, a dicynodont that managed to weather the storm. The Gorgonopsids were gone, leaving behind only their bones in the Karoo and Russia as a testament to their reign, the survivors' cynodonts. While the Gorgonopsids perished, another group of therapsid synapsids survived the Great Dying, the cynodonts. These were generally smaller, less specialized, and perhaps more adaptable than the Gorgonopsids. They likely possessed efficient burrowing behaviors that allowed them to escape the worst of the heat and environmental chaos. The cynodonts also had more advanced secondary palates, allowing them to eat and breathe at the same time, a crucial adaptation for a high-metabolism animal. It was from these small, scrappy survivors that the first true mammals would evolve later in the Triassic period. In a way, the extinction of the Gorgonopsids was a prerequisite for the rise of mammals. Had the Gorgonopsids survived, they might have continued to dominate the large predator niches, preventing the dinosaurs from rising to power in the Jurassic and altering the course of history entirely. But they fell, and the world passed to the archosaurs, the lineage of crocodiles and dinosaurs. Convergent evolution. The study of Gorgonopsids offers a masterclass in convergent evolution. Convergent evolution occurs when unrelated organisms evolve similar traits to solve similar problems. The Gorgonopsid body plan, the saber teeth, the robust neck, the ambush tactics, anticipates the morphology of the saber-toothed cats, Mesozoic, that would appear over 200 million years later. Smilodon, the famous saber-toothed cat of the Ice Age, is a placental mammal, separated from the Gorgonopsids by an immense gulf of time. Yet, natural selection molded both lineages into remarkably similar shapes, because the biomechanics of killing large prey with enlarged canines requires a specific set of adaptations. The boxy skull, the powerful neck muscles, and the gaping jaw gape are solutions that evolution stumbled upon twice. Comparing Innostrancevia to Smilodon allows paleontologists to test biomechanical models and understand the universal constraints of being a macropredator. Paleopathology and life history. Fossil bones often bear the scars of a hard life. Gorgonopsid specimens frequently show signs of pathology. Broken and healed ribs are common, suggesting that hunting large, heavy prey was a dangerous business. A kick from a parasaur or a toss from a dicynodont could easily fracture bone. There are also signs of infections in the jaw and skull, perhaps resulting from broken teeth or wounds inflicted by rivals. These injuries tell a story of resilience. These animals survived severe trauma, suggesting robust immune systems and a physiological capacity for rapid healing. Some skulls show tooth marks that match the spacing of other Gorgonopsid canines, direct evidence of face-biting behavior. This behavior is seen in many modern carnivores, from lizards to wolves, as a way to settle disputes without fighting to the death. The legacy of the Karoo. The Karoo Basin in South Africa remains the most important site for understanding Gorgonopsids. The stratigraphy there is so detailed that paleontologists can trace the rise and fall of different Gorgonopsid species layer by layer. It allows for high-resolution biostratigraphy. We can see how species turnover occurred, how different morphotypes replaced one another, and how the ecosystem responded to smaller environmental perturbations before the final cataclysm. The research conducted in the Karoo over the last century has moved Gorgonopsids from obscure curiosities to well-understood components of Earth's history. Museums in Cape Town, Johannesburg, and around the world house these collections, which continue to be studied with new technologies like CT scanning and 3D modeling. Technological advances in study. Modern technology has revolutionized our understanding of these ancient beasts. In the past, we only knew the outer shape of the bones. Today, with high-resolution CT scanning, paleontologists can look inside the skull without damaging the fossil. They can reconstruct the brain cavity, the inner ear, and the routes of nerves and blood vessels. This paleoneurology has confirmed the importance of smell and balance in Gorgonopsids. Finite element analysis, FEA, is another engineering technique applied to fossils. By creating a digital model of a Gorgonopsid skull and applying virtual forces, scientists can simulate a bite. These studies have shown that the Gorgonopsid skull was incredibly resistant to the vertical forces of biting, but perhaps weaker against twisting forces. This supports the slash-and-pull hypothesis of hunting, where the predator sinks its teeth in and pulls back, rather than shaking the prey. Gorgonopsids in popular culture. For decades, Gorgonopsids were relegated to the shadows of popular culture, eclipsed by the dinosaurs. If they appeared at all, they were depicted as sluggish, sprawling lizards. However, in recent years, they have experienced a renaissance. Appearance in documentaries like Walking with Monsters and the TV series Primeval brought them to a wider audience. They are now recognized as dynamic, terrifying, and sophisticated animals. This shift in public perception mirrors the scientific shift. We no longer view the Permian as a prologue to the dinosaurs, but as a fascinating and unique chapter in its own right. The Synapsid Empire is now appreciated for its complexity and grandeur. Comparative anatomy with dinosaurs. It is instructive to compare the Gorgonopsids with the theropod dinosaurs that would eventually replace them as top predators. A Gorgonopsid like Innistransevia and a dinosaur like Allosaurus were both bipedal or semi-bipedal killing machines, but they operated differently. Theropods were obligate bipeds with bird-like respiratory systems, air sacs, that made them lighter and arguably more energetic. Gorgonopsids were quadrupedal, heavier, and relied on a diaphragm-based breathing system, ancestral to ours. The dinosaurian lineage invested in agility and lightweight construction, while the Synapsid lineage, at least in the Permian, invested in raw power and durability. Ultimately, the archosaurs, dinosaurs, won the race in the Triassic and Jurassic, perhaps because their respiratory system and water retention capabilities were better suited to the hot, dry world left behind by the Great Dying. It would take the asteroid impact of the Cretaceous 186 million years later to knock the dinosaurs off the throne and allow the synapsids, now mammals, to reclaim the world. The meaning of stem mammal. The term mammal-like reptile has been discarded by modern science because it implies that mammals evolved from reptiles living today, like lizards or crocodiles. They did not. Synapsids and sauropsids are sister groups. A Gorgonopsid is not a reptile, it is a member of the mammal line. If you were to travel back in time and look at the biochemistry of a Gorgonopsid, you might find urea-based excretion, like mammals, rather than uric acid, like reptiles. You might find a glandular skin. You would see an animal that feels hauntingly familiar, a twisted reflection of the mammalian blueprint. They are our great uncles, a side branch of our family tree that grew mighty and then was cut short. Studying them helps us understand the deep roots of our own biology. Our single temporal fenestra, our differentiated teeth, our upright posture, these are heirlooms inherited from the synapsid experimentation of the Permian. Geological stratigraphy and dating. The precision with which we know the Gorgonopsid era relies on geochronology. Radiometric dating of volcanic ash layers, tuffs, found within the sedimentary sequences of the Karoo and Russia, provides absolute dates. This allows scientists to pin down the appearance of the first Gorgonopsids to the Wardian age of the Middle Permian and their extinction to the Chongqingian age of the Late Permian. Correlating these dates across different continents allows for a global reconstruction of the Permian world. We know that when Inostrancevia was hunting in Russia, similar Rubigen Gorgonopsids were hunting in South Africa. This global distribution speaks to the interconnectedness of Pangaea. The role of continental drift. Plate tectonics played a major role in the evolution of Gorgonopsids. The formation of Pangaea reduced the amount of coastline relative to land area, creating the arid continental interiors. It also allowed for the free movement of fauna. There were no oceanic barriers between Siberia and South Africa. This cosmopolitan distribution meant that when the extinction event hit, it hit everywhere. There were no isolated island continents to serve as refuges. The connectivity of the world, which had facilitated their spread, ultimately facilitated their demise by ensuring the environmental collapse was total. The diet of the giants. While we focus on predation, the specifics of consumption are interesting. Gorgonopsids had a hinge in their jaw that allowed for a wide gape, essential for clearing the tips of the sabertooth. However, their lack of grinding teeth means they could not process bone or tough plant matter. They were likely specialists in soft tissue. They were meat shearers. This dietary specialization makes them vulnerable. An animal that can crunch bone, like a hyena, can scavenge and survive on scraps. An animal that needs fresh meat is more susceptible to population crashes in prey species. This hyperspecialization is a recurring theme in extinction. The specialists die, the generalists survive. The cynodonts that survived were generalists. The Gorgonopsids were specialists. Evolutionary dead ends? It is common to view extinct lineages as failures. This is a mistake. Gorgonopsids were incredibly successful. They dominated the terrestrial ecosystems of the planet for roughly 15 to 20 million years. That is a vast stretch of time. For comparison, the genus Homo has been around for less than 3 million years. Gorgonopsids were perfectly adapted to their environment. They only failed because the environment changed faster than evolution could keep up. In evolutionary biology, fitness is relative to the current environment, not the future one. In the context of the late Permian, the Gorgonopsid design was the pinnacle of vertebrate engineering, the subfamilies. Taxonomy within Gorgonopsia is complex, but broadly, they are divided into groups based on cranial characteristics. The Gorgonopsinae, including Gorgonops, represent the standard form. The Rubigini, as mentioned, were the robust, heavy hitters of Africa. Another group, the Inostrancevinae, includes the Russian giants. There are smaller, more basal forms as well. Constant revision is occurring as new fossils are found and old ones are re-examined. Some species named in the early 20th century have been synonymized, recognized as merely males and females of the same species, sexual dimorphism, or different growth stages, ontogeny. Understanding ontogeny is crucial. A juvenile Gorgonopsid might look like a different species than an adult, due to the way the skull changes shape during growth. The aesthetic of the Permian. If we could stand on a Permian ridge and look down, the scene would be alien. The light might be diffracted by dust and heat haze. The vegetation would be dominated by darker greens of gymnosperms, lacking the bright flowers of today. In this landscape, the Gorgonopsid would move with a heavy, purposeful stride. The silhouette would be distinct. The high shoulders, the low-slung head, the tail trailing behind. It was a dragonless world ruled by beasts that were something other. It was the empire of the Synapsids. Conclusion. The Gorgonopsids of the Permian period represent a spectacular peak in the history of life. They were the Earth's first experiment with the saber-tooth predator design, an experiment that produced terrifyingly effective hunters. They highlight the dominance of the synapsid lineage long before the age of dinosaurs. From the swampy beginnings of the Carboniferous, through the sail-backed pelycosaurs, to the agile and powerful therapsids, the road to the Gorgonopsids was paved with evolutionary innovation. Their anatomy reveals the transition from reptile-like ancestors to mammal-like descendants, bridging the gap between two great worlds. Their extinction serves as a somber reminder of the fragility of life in the face of geological upheaval. The Siberian traps and the Great Dying erased them from the face of the earth, but they paved the way for the survivors. The cynodonts, scurrying in the shadows of the Gorgonopsids, carried the genetic torch that would eventually ignite the mammalian radiation. We, as humans, are the distant inheritors of that legacy. When we look at the skull of a Gorgonopsid in a museum, with its terrible sabers and boxy snout, we are not looking at a stranger. We are looking at a lost cousin, a testament to the incredible diversity and resilience of the synapsid line. The Gorgonopsids are gone, but in the deep history of our own DNA, their story persists. They were the kings of the Permian, and for 20 million years, they were the masters of the world.